like explore data and all of that. And NumPy is a bunch of, NumPy itself is like this big library with a bunch of shelves inside, and I'm just giving a sort of visual explanation to explain what I'm saying. It's actually not a physical library. It's a bunch of code somewhere that contains other bunches of code. I don't know if that makes sense. So there are things that would help you, like with your data manipulation, manipulating numbers and arrays and doing some cool mathematical stuff, so you don't have to start writing a function to find variance and mean and the maximum number or the minimum number. There's already a function for that, so you just call it. But I can't just call it inside my code, because my code, if I just say mean of something, I just say var of something, my interpreter has no idea what that is. It's going to tell me that that function is not defined, or that variable. It may think it's a variable and tell me that there's no such variable or there's no such function. So when I say import pandas as PD, I'm telling it, go and find this pandas package and download it into my code. So this line now represents just pulling in every single piece of code in pandas and putting it at the top of my notebook, right? Then this line is just going to pull in every single piece of code that is inside the NumPy package and putting it at the top of my notebook. So when I reference something from this NumPy package, the interpreter knows what I'm talking about. Okay. So here we could just import matplotlib if we wanted to, and we'll be able to access pyplot inside matplotlib. But instead, since we know we'll just be using the pyplot aspect of it, we just import matplotlib.pyplot. So you're telling it, open matplotlib, find pyplots, and bring just pyplots in here. Then when you say as PD, as NP, as PLT, we're just assigning it a nickname that we will be referring to the package as for the rest of our code. So instead of always typing out pandas.readcsv, I just type pd.readcsv. Is that clear? Does it make sense now?
Yes, sir, it's clear,
All right, beautiful. Let's proceed. Okay, so we've imported our dependencies and we use pandas to import the data sets that we're going to use. We'll figure out which one we're using later. These are all the data sets from the unsupervised learning course that was assigned over the week. Excuse me. Okay, so we already have some problems in here. Let's just take the first one. It says you work for an agricultural research center. The manager wants you to group seed varieties based on different measurements contained in the grains data frame. You also want to know how your clustering solution compares to the seed types listed in the data set. And they are letting us know that's the variety number and variety columns. Okay, so now this is not a typical unsupervised learning problem in real life, because we already have the seed types listed. So this is a label, right? We're going to be doing an unsupervised learning. We're going to be using this unsupervised learning, but ideally, you'd most likely not have this. You'd have to fly blind. That is unsupervised learning. You have to fly unsupervised. Anyway, let's get started. So, what's our first step from supervised learning, guys? What's the first thing we do okay, so we're using, that's grains. Okay, this is what we're using. Let's comment this out. Okay, so we're using the grains data set. Let me run this. So what's the first thing? Someone unmute your mic and tell me, please. What's the first thing you do after you've imported your data set before you get into the interesting stuff? Come on, tell me. Nobody?
You check the first 5 items, and so grains go to df.head.
Okay, df.head. And what is that under?
It will read the first 5 rows of
Yes, I get that. But what step is that under? You know, we have like different steps that we were going through while doing supervised learning. So broadly, what step is df.head? What does it fall under? Do you remember? Okay, that's fine. So that would be, yes, thank you very much, Esther. That would be EDA. Who can remind me what EDA stands for? Come on, guys, don't be shy.
Data analysis.
Beautiful, thank you very much. Exploratory data analysis. So you explore your data, you analyze your data. You basically, we don't know what is inside grains, right? We want to figure out what we're working with, because you don't just start typing a bunch of Python commands and stuff. You need to know what's, oh my God, my apologies, guys. Naughty kids. So you need to know what you're working with. We know what the problem is, but we need to know what we're working with to know what to do to, you know, this to get there, right? So exploratory data analysis. Now, grains, right? Yes, grains. Someone mentioned .head. And we know that that gives us the first 5 entries, the first 5 rows in our data set. And like I said last time, it's customizable. You can add a number in here into the bracket. So you could come here and type 10 if you wanted to, or 7 or 6, and to give you that number of first entries. Conversely, you could use .tail, and that would show you like the bottom 5 instead of the first 5, the last 5. And you can also customize tail with a number. All right, so we have a couple of columns that don't have any names. So, and this is something that you can have in real life data. You may not know exactly what these features are, you know, it may not be fully interpretable. Okay, and then we have 2 columns that represent the label. We have variety and we have variety number. This is like, what's the word? Encoding, yeah? Is like the encoded label. So basically the same information here is here, but this is just in numerical form. All right, what else? Do you guys, what more do you want to do to explore this data? Anything else? Just head, is .head enough? Should we move
No,
on?
is df.info to check the various
All right. The info gives us like a summary, a general rundown of the data that we're working with, right? You guys remember from supervised learning. So it tells us that our data is a pandas data frame, tells us the type without us having to call type on grains. And it tells us that we have 210 entries, numbered 0 to 209, and we have 9 columns. That's typically 9 features. But in this case, we have 7 features and 2 labels, right? And it tells us if we have any known values, if we have any empty cells, and we don't. This is pretty clean. And it lets you know what data type each of these columns contain. So you can see that these all contain floats, that's all features. And then the variety number label contains integers, and variety contains the object type, which would be like text, you know, whether it's a sentence or a character or whatever, it should show up as an object. All right, anything else? Or are we good? We've done .head, we've done .info. Anything else? Shall we move on? Come on, guys. Okay, let's carry on. So it's always a good idea to describe, you know, to see what the statistical distribution of your data is. This step just to reiterate what we did during supervised learning, this step helps you, it helps inform what you do during pre-processing, right? Because there are a bunch of things that could be covered during pre-processing. But this lets you know, it gives you some sort of information into what you should do and what you should not worry about. For example, we can, looking at the mean across each of these features and looking at the standard deviation and looking at the mean and max values gives us a lot of insights. The mean gives you some sort of idea of distribution, right? So this already lets you know that these two have some similar distribution, especially in magnitude. And this one is way smaller, like the scale is going to be much smaller in this one compared to this. If the mean, if the average value here is 0.8 and the average value here is 14.8, this is 14.5. So it tells you across what, the spread is like. Standard deviation does the same thing as well. This has a standard deviation of 2.9 and 1.3. This also gives you a slight insight into the variance, because variance and standard deviation have a very close relationship, right? So it gives you some insights into the level of variance across this particular feature. So you see that these ones have comparatively high variance, and this has very little variance, 0.02. So that means most of the values are around 0.8. And by the time we check the mean and max values, we would see that that actually stands. Minimum value is 0.808 and the maximum is 0.918. That tells you that this is right in the middle, and the change, the deviation from the mean for each of the entries is just 0.02, right? Then this has a minimum of 10.59 and a max of 21.18. That already tells you how different they are in scale. First of all, all the values for this feature are between 0 and 1, right? In fact, between 0.8 and 0.92, not even between 0 and 1. That's how tiny the spread is. Between 0.8 and between 0.8 and 0.92. That's all the values here falling. This is on the far right of this one. Starts at 10.59 and falls between 10 and 22. Way over there. So first of all, it's very far from where this one is. If you check the distance on the number line, then it has a much wider spread. All of this is between less than half of a unit, and this spans across like 11 units or 12 units, right? So you already know that the scales are different across some of these features, and that is just looking at two features. We have a bunch of them here that have different spreads and stuff. So that already lets you know that if you're working with first of all, it's best practice to do what I'm about to say. But you could also, depending on your level of expertise, decide that that step is unnecessary because of the model that you're going to be working with. I mentioned during supervised learning that there are certain models that are very sensitive to distance and scale and magnitude. So looking at this, you already know that the spread here is going to affect such models. So you make a mental note that in your pre-processing steps, you should include some sort of centering and scaling, or normalizing, one of that's basically any of the ideal steps that would fall under the category of centering and scaling should be done to these data sets. If you're going to be using, well, first of all, best practice, but then further, if you're going to be using anything that is affected by distance and magnitude and scale. Okay, that's a lot of words. So we've done the describe, we've looked at the statistical summary of the data. Is there any other thing that you want to look at? Okay, we can move on. We can always come back and check if there's certain information we want to find out about the data, right? Okay, then up next is pre-processing, and we know what this is, right? Does anybody not know what pre-processing is? If you don't, just raise your hand, I'll hear it and I'll speak out. I don't need to see who is asking. Okay, seems like everyone does. All right, so to pre-process our data, now we know that we already know that we're tackling an unsupervised learning problem. So by definition, we do not need labeled data. We need unlabeled data. So we need to get rid of those labels, isn't it? So the first thing we should do should be to separate our features and labels and only work with the labels, right? So let's separate features and labels. Okay. All right. You guys work with me. How do we do that? Let's define our features as X. What will X be? We've looked at the data. We know the columns contained. So what will our X be now? How do we define our X? Talk to me, guys. Come on, come on. Echo names. Come on, guys. There are 20 of us here. 21 now. Yeah, anybody? Okay, we're running out of time. Don't worry. And
You
yes,
can drop the Y future. That's the target area. We can just use dot drop.
all right. So
the
that's on brains, right? Yeah. I'm with you. Don't mute your mic. Come on. Let's finish the line. Come on with me. Are we on the right track?
Can you hear me? Can
I
you
can
hear
hear
me?
you. Yeah.
Sorry, I'm joining now. I'm just joining, so I don't really know the target, but
Oh,
I know
okay.
this to be target.
All right. Let me go back up for you.
Once it
Okay. So
drops
this is
6,
what our data looks like. We have 7 features labeled 0 to 6, and then we have these two columns that represent the same information basically. So these are our labeled columns. Good. Okay, let me just go ahead. So since we're dropping 2, we're going to put them in a list, and that is variety number, right? Variety number and variety, if I'm not mistaken. Guys, during the last class, I mentioned 2 ways to name the columns you want to drop using this dot drop. Who can remind me of the second one? Instead of calling the other way of doing it, instead of calling the names of the columns and then doing axis equals 1. Who can remind me? Does anybody remember? Was anybody there? It gives you the
You can
exact
just
same
use
result.
columns.
Yes,
Columns
thank you very
equal to
much.
the list of columns.
Beautiful stuff. So that's the second way. Someone was saying something about finding alternatives when you attend breakout sessions. So yeah, instead of putting this, you could remove this and just say columns equals, and it give you the exact same output. Okay, and who remembers why we add dot values? What does dot values do to this? Anyone?
It convert it to a numpy array.
Beautiful stuff. I love this. I love this. All right. So if you call this without dot values, it just gives you, it makes X another pandas data frame. So, you know, and it would still work. Funnily enough, you would still be able to train with your pandas data frame. But best practice, numpy array, right? If you want, you can still try without values, experiment. That's what this is about. Experiment, break your code base and come back. Break it, find out where it broke and fix it. But like I said, it would work even without advice. But this converts it to a numpy array. Yes, someone is raising their hand. I'm coming. Let me see what that is. Kazim, you have a question?
Yes, I just want to ask, do we need to normalize, because after we passed through dot describe, we saw that uh, the values, like I'm thinking, is it possible we normalize so that the maximum value will be, let's say, 1, like the numbers will be between 0 and 1. So I don't know
Yes,
if
yes.
I'm correct. I just want to.
Yes, you're on the right track. I went into this long rant about it, explaining how we had ways that to describe this. Explaining how the features had different spreads across them. I was using this and this, for example. So this one is just between 0.8 and 0.92, while this is all the way down between 10 and 22. So we have to bring them to be on the same scale. We have to make them statistically comparable so that our model doesn't give preference to one feature over the other. So yes, you have to use something in the arsenal of tools for centering and scaling, right? So you could scale, you could use abs max, right? There's min max, there's normalizing actually. You could use that. They all generally do the same thing, centering and scaling, but they do them in different ways. So it could bring your scales, all your scales to be between 1 and 0, or make the mean of all your features to be 0 and the variance to be 1. So if the mean is 0, it means all of them are centered around the origin. They're all centered around 0.
Yeah.
Or it could make your values be between -1 and 1. Have I said that already? But yeah, so yes, you're on the right track. That's going to be one of our pre-processing steps.
Thank you.
All right, where were we? So we've selected what X is going to be. Let's bring out our feature. Our feature is variety, right? Yeah, variety. Let's just bring it out as an array of its own. So let's call that variety and make it equal to grains variety dot values. Okay, all good. And let's see what our X looks like. And just look at it here. Is that big X or small X? I can't remember. Okay, so we see that this is a numpy array with the values for each of those features. Okay, and as stated, next we need to do some sort of centering and scaling. Right? So whichever, that's too big. Whichever tool you prefer or that will work best for, and that's actually would require subject matter experience and also knowing how each of these tools work, right? That is deeper than this particular course for this week. So let's just use standard scalar, the most popular of them all. So who can remind me where we import standard scalar from? Fastest fingers. Where do you get it from?
From sklearn.preprocessing.
Beautiful. Pre-processing. That is where our standard scalar falls. So from sklearn. So the person that asked the question about the whole importation thing. So this is another way that you can import something. You can say from sklearn.preprocessing import something. So you tell it to find sklearn, inside sklearn find preprocessing, then inside preprocessing find, whatever it is that you type after this. right? Now you could do that as well by saying import sklearn.preprocessing.standard scalar. But that would mean that each time you call it, you'd have to call it as sklearn.preprocessing.standard scalar. And that is just a lot of words. So if you do from this import and you just call that name, right, just that name that you're trying to import, then you just have to call it with that name. So if I call standard scalar, then when I want to create an instance of it, I just say, you guys remember how to do this as well. Let's create an instance. You say scalar is equal to standard scalar, instead of calling sklearn or preprocessing the standard scalar, right? Okay, so let's create an instance of this, and since we're not splitting data here, let's just fit transform as well. So we're doing this on just our x. So let's call the output x scaled. I want to say x scaled is going to be equal to scalar.fit transform. Oh, let me copy from it. Scalar.fit transform, and we're calling that on x, right? And our output is going to be scaled version. So if we come after this and we say we just call x scaled, we see that the values of the numbers have changed, right? So we had 15.26 here. Now we have 1.42 yada 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 times 10 raised to the power minus 1, right? So this is 0.142 yada yada yada, and so on. So they're all equals now. They're all mates. They cannot fight on an even playing field, right? What other steps fall under preprocessing from our last skinny? Like general steps. I don't need the exact tool that we use. General steps on the preprocessing. Okay, let me just jog our memory. So we would have generally steps that will fall under data preprocessing would include encoding, whether feature encoding or label encoding. But in this case, when we looked through the data, we didn't have any categorical data as part of the features, so we don't need to encode anything. And the label was already encoded for us. Although we don't need the label here, so we're not even paying attention to that right now. We'll use it for something else later. I'm sure you guys saw it in the course, but we're not paying attention to that. Then another thing we'll do would be handling missing data, right? So either dropping or imputation. But when was that? Yes, when you looked at our info, we could see that there was no null value. So we don't have any missing data to either drop or impute. And then, of course, there's centering and scaling, which we have just done. So since we don't have any other pre-processing steps, let's move on to our model selection and training. Okay? All right. For this one, let's use k-means. Again, one of the most popular of them all. So from sklearn, give me a second. Okay, where are we? Yes, k-means. Where do we get k-means from? Who can remind me? I started giving expo already.
sklearn.cluster.
Cluster.
Thank you. Now, let's always pay attention and be careful not to mix up this one and this one. Right? Did anybody, get that confusion within the week? Nobody. All right, that's good. So KNN is k neighbors classifier, sorry, k nearest neighbor, And when we are importing it, we import it as k-neighbors classifier for classification. There is actually k-neighbors regressor, but that doesn't concern us right now. So KNN is k-nearest neighbors, and k-means is something else. KNN is for supervised learning, mostly used for classification problems, while k-means is unsupervised learning used for clustering. So k-means clustering, KNN classification. Okay. Okay, so from sklearn.cluster, we are importing k-means, right? Okay, so what I want to do here is in the real world, yeah, you most likely don't know how many clusters to work with. So we can't just go right in and instantiate k-means with n clusters of a certain number without knowing what we're working with, right? So we're going to use the elbow method. I'm sure you guys came across that this week. We're going to use the elbow method to try to figure out what would be the optimum number of clusters, right, for this particular data set. So we'll do that using the inertia values from k-means. So let's create an empty list. We're going to use a loop, just like we did in supervised learning, and we looped through various different models to find out which one performed better on the base value. And we found the best on base value, and then we tried to tune the hyperparameters to make it even better from there. So that's something similar to what we're doing here. We're just going to use a for loop, nothing crazy. So we're going to create an empty list for inertias, and then we would say, let's use case, let's use a range from, let's say a range of 1 to 7, right? That should work. So for those that are not familiar with Python before now, I said range of 1 to 7, but I wrote 1, 8. That's because this range is going to stop just before the last number. So if I say range 1, 7, it's going to give me 1, 2, 3, 4, 5, 6. Sorry, 1, 8 is going to be 1, 2, 3, 4, 5, 6, 7, and stop once it sees the number 8. So it's not going to include 8. It doesn't include the last number. It is going to give me a list from 1 to 7. Yeah. So now let's build our loop. So I'm going to say for k in case, this cool stuff that we can do in Python. C++. Rubbish people. So k in case, let's say our model is going to be, so each time we go through a value of k, it should create an instance of k-means with n clusters given as k, right? So the first time around is going to be 1, the next time is going to be 2, etc. until it gets to 7. Then for each instance, after selecting a value of k, we want it to fit on our scaled values of x, right? Because we're not fitting on x because we already scaled. If we were going to fit on x, we wouldn't have scaled to begin with. So inertias now should include, I'm going to append to this empty list that we created here the inertia value for each run around. So when k is 1, we get the inertia value and append it to this. When k is 2, we append that. When k is 3, we append that until it runs through the range 1 to 7, right? Okay. And then let's visualize it so we know exactly where we're going. So let's call the graph of the inertia. Okay, so call PLT. The person that asked the question about the importation. So now instead of calling pyplot or Yeah, instead of calling pyplot, or instead of calling matplotlib.pyplot, I just call plt, the nickname that I gave it. And then I say plt.plot. What is this? That was strange. plt.plot, plotting, on the case on the x-axis, we want inertias on the y-axis, and we want it to use a circular marker for each point. So let's that should hold. That should be all. Right. Anything else? That's it. Then plots the x label. If there's any part of this that anybody doesn't understand, just raise your hand and ask a question, okay? Let's make this number of clusters. And then let's plot inertia on the y label. Okay. And show me what we've done. Moment of truth, guys. Oops, sorry. All right, and we have our initial diagram. So when we have one cluster, obviously we're going to have the most inertia. And remember, for inertia, lower is better. The lower the inertia, the better for us. So for one, we already know that is bad clustering. If it's one cluster, it's just the raw data. So the inertia is very high. It's above 1,004. Then for two clusters, we have just about 600. So let's say 680 is somewhere close to 700. Then for three, by the way, you can see these values from model.inertia. Right, for each of the fitted models, you can call model.inertia to see the actual number. Now, to choose the optimum number of clusters, we go for the elbow. And generally speaking, it's where the reduction in inertia becomes less drastic, less dramatic. When we go from one cluster to two clusters, there's a steep reduction. It drops all the way from 1,000, maybe 1,005, thereabouts, all the way down to 680 or something. That's a drastic leap. And then from 2 to 3, it drops all the way from that to about 400 and something, right? But then after 3, the decline is not as dramatic. If we remove, let's remove these all markers. So it's not as clear. Okay, so if we remove the all markers, after 3, it looks like it's just a straight line and not a steep one at that, see. So that tells you that this is about good enough, right? This is tight. This gives you the trade-off between having clusters that are tight and having clusters that are not too many. We have as few as we can, we're having as tight as we can. That is here, that is 3. Okay, so we've gotten our number of clusters. Should I put that back? Let me put the markers back. I think it looks better that way. Okay, moving on from that. So we've chosen 3. Does anybody have, is there any reason, does anyone have a reason why 3 should not be our bride? Speak now or forever hold your peace. Yep, do we all agree with 3? Okay, let me come to this page. You can react. I've seen you guys are scared of your mics. You can react if you agree with 3. Do you agree that 3 is the optimum cluster? I saw something now. Kiwi-san, it's nice to have you back. All right, let's move on. Where are we? Yes, this page I'm sharing. Okay, so we've chosen our, am I on the right page? Yes, I am. We've chosen our number of clusters as 3, is right there at the elbow, and we've already defined what the elbow is, where there stops to be a steep or dramatic decline in inertia. So next up, we want to now train that actual model with 3 clusters, right? So let's give it a new name. Let's not call it model so that we don't have, some mix up there. So let's call it KMC for k-means clustering, and we're going to call that k-means with the instance of k-means with number of clusters equal to 3, right? Now we're going to call labels. Should I do fit predict? Yeah, let's just fix into one line. We're not splitting data anyway, so there's no leakage. So we're going to call KMC dot fit predicts. And for most of these scikit-learn tools that have fit and predict and fit and transform, for a lot of them, not all. Which one is that? There's one of them that only has fit transform, doesn't have fit and transform. Which is that? Which is that? Which is that? I can't remember right now. Anyway, for most of them, you could fit then transform, or you could do both in one go. Fit transform, it fits and transforms at the same time, or fit predict. Sorry, for KMC or fit predicting. It depends on the model. Now, if you're working on a supervised learning model, I'm going to say it again. There's something called data leakage. So if you're using something that's what's the word? Something that transforms your data, right? Basically something that fits, anything that has a fit learns from your data. Something that learns from your data, you don't want it learning from the complete data set. So you should make sure that you split before you fit, whether it's standard scaler, whether it's some other scaling and centering tool, whatever it is, split first, because there could be data leakage. It learns from the full data, and then that information leaks into the model, and your model ends up memorizing instead of learning. Okay, proceeding. So we're going to do this on X scale, because why not? We've scaled it already. Okay, so labels now is going to contain whatever the label of whatever cluster that this KMC assigns to each of the entries in X scale, right? So it could be 0, 1, 2, 3, whatever, depending. But now, because we've chosen 3 as our number of clusters, it's going to be 0, 1, or 2, 3 clusters. Yes, there's something we can do. Since we do now in real life, we most likely will not have the labels. But in this case, Christmas came early, and we actually have the labels. So there are a couple of ways we could confirm that 3 is the optimum number. One of them is in one of those things that I showed you guys during EDA, right? Where is EDA? Yeah, EDA. Okay, let's go to the bottom here. Let's add another cell. So one thing we can do in EDA is Python. Let's check grains. So we know that our target is variety. Let's not use variety number. Let's use variety, so it's more interpretable. So let's call variety. Now, when we did dot head, we only saw comma width. I'm not sure what that is, but it's something, comma width. And we just saw a bunch of ones. And even if we extend this to 10, I don't think we'll see much more. Let's see. Yeah, still a bunch of comma width. So if you're looking at just the head, you might think that you just have one variety or two. Let's find out if that is true. So if we come to the variety column in grains and we call dot unique, you guys remember dot unique? It gives you an array of the unique what's the word? The unique options basically in this column. So we can see we have 3: comma width, rosa width, and Canadian width. Excuse me. And if you don't want to see what they are exactly, you just want to know the number, you can call .nUnique, and that gives you the number of unique items in this variety column. So that tells you that there are 3. So we're on the right track, right? We're on the right track. Choosing 3 as a number of clusters, because there are 3 here actually. And another thing you could do is maybe you want to check if your data set is balanced, which would be more, reasonable or more useful for a supervised learning problem, because then you know that you have to stratify your Y while splitting. So if you want to do that, you could call value counts. You guys remember value counts? You guys actually remember? I feel like I'm just talking to myself. Value. And that tells you the number of entries for each value, right? So yeah, this tells you that each of them has 70, so this is pretty properly distributed. Another way we could confirm. Should we do that? Well, we already have the information we have from here. Now, this is multidimensional. You could try plotting this, maybe pick 2 dimensions or something and try to do a scatter plot. You would most likely not get the information for real data sets. Some of the examples that were used during the course of the week, you'd see clear distribution between each cluster, but most times it's not that way. Most times it's just a bunch of dots, right? You know what? Let's try to do that. Let's do something like that here. So let's pick 2 values. So let's call x's. Let's give it the name of the first column. The first column is 0, right? So let's call that x's. And let's call this y's. This is just for visualization. Please don't confuse this with our actual x, okay? I'm just picking something that we can use to plot a graph, plot a scatter plot. And then let's use 1 as the first and the second values. Then let's call PLC that's scatter. X is against Y is no, let's not do that. Let's just plot this. And then PLC, let's show. Okay, let's see what that looks like. Yeah, no separation whatsoever, right? And there's very low variance across this one. Let's pick something with more spread. Let's pick something with better spread. Maybe it's the feature, this is 0. 0 has standard deviation of 2.9. I think this is the highest. This has standard deviation of 1.3, so that should be pretty varied. Okay, let's use this 1.5. Let's use 5. Yeah, that's better. That's a better spread. That is just a bunch of points, right? That's just a bunch of points. Okay, let's proceed. Where were we? Okay, I think someone raised their hand. I heard the sound. Who was that? Please ask a question. Yes, Ismail, go ahead.
This time. So can you hear me?
I can hear you. Go ahead.
Okay. You talk about data leakage when scaling our data. So I didn't understand that fact quite clearly. The reason why I'm asking is that when I'm doing my running my own notebook, I kind of scale my data before splitting it. So I kind of confuse in that part.
Okay.
Can you expand?
So yes, I will try to explain that. I hope I do a good job. So where did we scale? It's hanging. Give me a second. Yes. Okay, so this is a standard scalar instance, right? And to use it, we called .fit transform. You could call .fit, then call .transform. When you call .fit, whatever scikit-learn thing that you're using, when you call .fit, what it does is to learn the data or learn from the data. It learns the relationship in the data. So when you call this on a data set, it goes to find out what the mean of each column is, finds out what the variance is across each of the columns, and keeps that information. Then when you call .transform, it uses that information to transform your data. So it subtracts the mean from each of those numbers and does a bunch of manipulation so that the mean of the column is 0 and the variance is 1. That's for standard scalar. And for other tools that have .fit, they do the same thing. They pick up some information from your data and hold on to that information, and then uses that information to transform your data, right? So let's use this as an example. Let's use the standard scale as an example. We have this as our complete data set. Let's say for supervised learning now, this bottom part is your test data, and this top part is your training data. Okay. If you call scalar.fit on this entire data set, it learns the mean of all the numbers in this column and the mean of all the numbers in this column and the mean, like that all the way down, and the variance of all of them as well, right? And it keeps that information. Now, when it's transforming the data, it's using the information that it got from all of these, right? Now, by doing that transformation, it has added some information to your data. And this is how you would know. If you run your .fit on just this part, and then you transform your data, the numbers you would get would be slightly different from if you run .fit on all the numbers in this column. Why is that? Because the mean of these numbers, these 3, is definitely different from the mean of these 6, right? So if I subtract the mean of these 3, or rather, if I subtract the mean of these 6 from this one, and this one, and this one, and all of them, that is some new information that I've introduced to this data. So your model might pick up that, like I said, all of these things are happening mathematically. What the model is doing is math underneath the hood. So your model might, at some point, pick up that relationship, that there's some factor that has been subtracted by all of these numbers while it's looking at the training data sets, right? But now that factor is telling it that there are some other numbers that are missing somewhere that we're supposed to make the mean, up to this. I don't know, am I confusing you, or does it make sense? How do I put this? It's like, let's say you get let's say you're given a 3x3 puzzle, right? Those 3x3 puzzles that have 10 spaces and 3 tiny squares inside of them. If you receive a puzzle with just 8 tiny squares inside, you already know that 1 square is missing, even without knowing what the square is, right? That is some extra information that has been leaked to you. You now realize that something is missing here. So it's something similar here. Some data can be leaked to your model if you perform operations that learn on your entire data set instead of just the training data set. So if you perform it on just this, because what you're assuming is that this training data is all the data that you have. This is what you're using to train your model. Then this test data is real world data, is what your model is going to face when it goes out there. It has never seen it before. So you have to learn on just what you can see. And then whatever you learn from this is what you're going to use to transform every other piece of information that comes your way. So you learn on this, fit on this, you transform this, and you also transform this. So you don't pick up any information from here. Because like I said, if you learn the mean, if you solve the mean of this, it's going to be different from when you solve the mean from this. So if you solve the mean from all of this, you've picked up some information here. So even if you split it after solving the mean, even if you cut it off here, after you've gotten the mean and done your scaling, the subtraction that goes across it all has some information that came from here. And it is possible, it may not happen, but it may happen that your model picks it up and realizes, one little square is missing here, right? And then because it's all mathematical, it is possible that it can deduce what that information is and now know what your test set is even before seeing it, and it learns all of that relationship. So by the time you bring the test set, it's practically, it might as well have been trained on the test set. It's not new information any longer. It has, the information has been leaked, the question paper has been leaked to it, in some way or form. Does that make sense? I think that was Ismail. Ismail, did that make any sense to you? Or did it make
Yeah, a little bit, but I was kind of confused in the middle, but since we don't have much time, so we can just go ahead.
All right. What I'll do is I think I'll see if I can find some resources that explain it really good, and I'll share that in the channel. Okay. If I forget, please send a reminder. Just on the group, tag me and send a reminder so I remember to do that. All right. Unfortunately, we only have 2 hours every Saturday, and the time goes so quickly. Where does all the time go? Okay, where were we? We've done this. We've gotten our elbow. Okay, we're down here. So we've done the fit predicts on our scaled data. Yeah. What are we doing? I feel like I lost my train of thought. Okay, yes. So labels is going to give us the corresponding numbers for the clusters that each entry is associated with. Now, we're going to do something because we have the labels already. Because we've been given the labels, we might as well use it. So we're going to try to see how well this model of ours has, clustered them when compared to the labels we already know they're supposed to fall under, right? And to do that, we're going to use the pandas crosstab function. So let's create a data frame first of all. That is pandas data frame. And I'm going to create that from a dictionary with key, let's just call it labels. And then the value is also going to be labels. No need to complicate it. Then we would have the next key being variety. That's the name of our label, right? Yes, variety. We're going to call it variety, and the value is going to be variety. Is there anyone that doesn't know how a Python dictionary works? Because this might just look like a bunch of gibberish to you. Oh, sorry, I wasn't supposed to run that yet. What's that? This should be n clusters. Okay, so everybody knows what the Python dictionary is. That's cool. Cool kids. So next, let's call this city. This is going to be our course tab variable, and that's going to contain ed.course tab. We're going to cross tabulate. I'm going to cross tabulate labels. Against variety, right? Okay. And we will print cross tabulation to see what it looks like. Okay, let's go. What again? All right, there we go. So we can see that the clustering is, it's not bad. For 0, we have that for what our cluster puts, for what our model puts in the cluster 0, you can see it's mostly Rosa weight. So cluster 0 almost perfectly aligns with Rosa weights. There are 2 in there that are not Rosa weights. Sorry, give me a second. Sorry about that. Very rusty days. Okay, so the 2 in here that are not supposed to be, that should be under common weights, but that's okay. Like with the example with the kid, you see some orange inside the red, and you see some blue inside the green. You don't expect it to be 100% perfect. Okay, I think that's over now. Sorry about that. Okay, and then for 1, it mostly corresponds to comma width with, about 9 entries falling outside of it. And then for 2, it mostly corresponds to Canadian width with six entries out of the rest falling outside of it. All right, and just like with supervised learning, we can combine those steps into a pipeline. All right, and we know we get our pipeline from sklearn.pipeline. So from sklearn.pipeline, let's import make pipeline. During supervised learning, I think we used pipeline itself. Do you guys remember that one? This is an alternative. That other one was pipeline with a capital P. Yeah, pipeline. Or you could use make pipeline. So we're using make pipeline for this one because that's what was used this week. So let's learn new stuff. So let's create an instance of it, call it pipe, and then we'd say pipe would be make pipeline. All right, go ahead.
Yeah. So my question here is that what are the difference between pipeline and make pipeline?
I think they are more or less the same. I've actually not checked because they have. Okay, let's look at this here. If you call pipeline, you know what? We just have 4 minutes left. I'm sorry. You know what's going to happen? I'm going to let's finish this. So this is capturing the record, and then after it, we'll handle that question. We're going to look at the documentation and see if there's any difference. Okay, but they do the same thing. They do the same thing, and they take almost exactly the same arguments. So I think if there's a difference, it's little. If there's a difference, maybe it would be that I know that pipeline takes transformers and then an iterator. So it takes a transformer before taking your model. Well, I think make pipeline can mix them up. Okay, I think someone, do you have a question or you have an answer to the question? Go ahead, go ahead. Someone raised their hand. Yusuf. Go ahead. Yusuf, did you raise your hand by accident?
I didn't raise my hand, but I'm just going to take Yusuf's opportunity to remind you about the attendance.
All right, thank you very much for that reminder. Give me a second, guys. Okay, I'm dropping the attendance in the chat. If anyone can't access it, oh, it's not letting you speak. I wonder why. You can, if it's a question, you can type it. If you can't speak. If anyone can't access the attendance link, let me know. So we'll do the quick in and out. Okay, so like I said, you can use a pipeline for those two methods. We already made a pipeline. We already made pipelines during supervised learning class. So here we're just combining the scaling and then the model fit in one instance instead of doing the steps one by one. So this would probably be what you'd have in production. You'd have a pipeline where everything runs through. Yep. So we have pipe.fits and then let's call them pipe labels instead of labels. Pipe labels would be pipe.predicts on X. Now we're running it on X, not X scale, remember, because we're scaling within the pipeline, right? Okay, for those who can't access the attendance, I'm going to quickly drop it in the chat. It should be there for like 1 minute, so run and click it so that truant students won't get the better of us, All right. Run, guys. Hurry. Okay, where are we? Yeah, we'll fit our model and we'll put our predictions. So let's compare it with what we had here. Let's just copy this. So we're still going to be comparing it against variety, but now we're using pipe labels instead of labels, right? To see if it performs as good. Okay, so let's call this df2 and we're going to be taking this from pipe labels. And this is going to be pipe labels.
Hello?
Yes, go ahead.
Okay, yes. Good evening, sir. My question is is not really related to the topic we are doing, so I don't want to disturb the class. Maybe I can have it at the end of the class.
Okay, that's fine.
Okay, thank you very much.
Please don't forget, I think I'm almost done. Okay, let's confirm that everything is in the chat. Oh, okay, I'm going to type my name in the chat. It's long, but it's the same name that's showing on my Google account. Okay, so my name is Grace Monkey Jonathan. Let's leave the middle name out so that you don't use up your characters. There you go. Okay, where are we? So we have df2 pipe labels. It's using variety, and let's use CT2. So we don't replace the CT we already have. Pipe labels. This will be df2. and we're printing CT2. All good. All good. Let's see what we have. And then labels. That's right, isn't it? Oh, DF2, yeah. All right, let's compare. Let's move this down here. Oh, it's hanging so bad. Okay, so this is without the pipeline, and this is with the pipeline. Okay, let's bring it down one. Okay, yeah. Let's see what we have. All right, so we have basically the same thing. The clusters are just shuffled. So same distribution, 462.5 down here, 66.60, same thing, and then 0 to 65. So yes, if you don't lose any accuracy or any information by putting it in the pipeline, it works just the same way. As long as now, bear in mind, while I was defining, where is it? Yes, while I was defining the pipeline, I used scalar and KMC. I just called that. The reason I'm able to do this and not get an error is because further up in our notebook, we already defined scalar as an instance of standard scalar and KMC as an instance of k-means clustering with 3 clusters, right? We have, where was that? I'll shuffle this thing up. I'm sorry, guys. Yes, here we have KMC here.
Please, can I see where you imported the scalar?
Yes, that was when we did our pre-processing. That was up here. Here, we imported standard scalar and we created an instance called scalar. So it's this scalar, this same scalar that I called inside the pipe. Right, there is a pipe here. And then it's this same KMC that I created earlier that I called inside here. So if you've not created an instance of these things already, you have to come, before this pipe to say scalar is equal to a standard scalar, and then KMC is this. So because it's the exact same instance that we used in our mini steps, that's why we're having the exact same clustering, okay? And then if we're to do this without scaling, don't worry, I'm not going to, let's just copy everything here. But now we're going to do it without scaling. Let's see what the difference is. Remember, k-means is distance-based, so the difference in scales and distribution affects it. So instead of using x scaled, let's use x. So let's call this, yes, who is that? You can ask or answer. Let's call this labels unscaled. Right? Yeah, labels unscaled. So we're calling this on x instead of x string. Then let's use df3 now. Then this is going to be labels unscaled. Oh, I copied again, sorry. This will be labels unscaled. We're still checking it against the label that we had. And this is going to be df3. This will be ct3. This is ct3 as well. This is also going to be df3. And this will be labels unscaled, right? I don't think I missed anything this time. Let's see if the interpreter agrees. Beauty. All right, so here we're having as much as 9. We have 12, as much as 12 falling out of the distribution here. So we can already tell from that this is worse. I think the maximum we have here is 9 across the label and 8 across the 9 across our cluster and 8 across the label. Here we have 9 missing here. We have 12 missing here. Ooh. Then we have 10 here and 10 here as well. So yeah, that tells you that scaling actually has an impact on these things. Okay. I don't know. Should we go into PCA? I would have liked to perform PCA on this same data set, and then we should also do data dimension reduction just in there. Let me see how many people are still on the call. Okay, 21 people are still here. All right, then let me quickly run through it. Sorry, somebody raised their hand. Who was that? Okay, Yusuf, I raising your hand so I don't forget to ask answer your question. Or do you have something else to ask? All right, that's fine. You can keep your hand raised, it's fine. Isaac, I just saw you cry. Do you have somewhere to be? Isaac, is there a problem? Oh, you didn't know I was back on this other tab when you were crying. I saw your tears, man. Don't worry, it's fine, We've all been there. Okay, let's move on to PCA. I hope we're all good up to this point. So PCA is principal component analysis. I'm just I'll leave going into the theory and all of those explanations. I hope the course was sufficient to explain that. If not, we can have that discussion afterwards. So let's go straight into the Python of it. So we get PCA from decomposition. So from sklearn dot decomposition section. I'm going to import PCA. Then we just create an instance of PCA. Just call it PCA is about PCA. And then we call PCA.fit. Now we're going to call it on the scaled data. Now, PCA is a tool that can be used for a bunch of stuff. It's actually a very cool tool. It helps you to transform your features into things that are, more useful, right? But the downside is that you lose the interpretation of your features. So if you had features of fruits and you had color, taste, shape, and stuff like that, when you run PCA on those features, the columns no longer represent color and taste and shape, right? They may have some relationship to them, but you lose the interpretation of the features. You can't tell which feature is this anymore. That's the downside. But it makes them more useful for your model. And then it's also used for dimension reduction, which is what we're going to do next. In that, when you have, like I mentioned earlier, the number of features you have tells you the dimensional space that your entries exist in. So if it's 2 features, it's a 2-dimensional space. If it's 1,200 features, it's in 1,200D space. That's what you have. Now, you're going to have data that covers a bunch in real life. If you're collecting data of pupils or data of students or patients, you collect a bunch of things: blood group, mother's maiden name, age, address, hair color, eye color. So depending on what you're looking for, a bunch of those features mean nothing. A bunch of those features are just noise, right? They just make the work more difficult for your model. And then in some cases, some of those features are also collinear. They're either collinear or they're very closely related, right? Collinear means that they are on the same line. It means that they have a strong relationship. It means that, okay, let's use an example of, let's say you're collecting data that has to do with people. If you have, let's use something that is a no-brainer. Let's say you have weight in pounds and weight in kg. There is no need to have weight in 2 metrics. right? You don't need to have weight in two measurements, because if weight is increasing in pounds, it's definitely increasing in kilogram. They have a very straight line, a very strong positive relationship. So your data could contain such information, features that are very related or that have exactly the same information. PCA helps you with that. It can help you reduce your dimension by removing things that you don't need. But this one, it does it in the sense that it helps you remove features that don't tell you so much about your data. They don't describe a lot of variance. Like when we plotted this, and we used one here, when we used one to plot this, you could see that using that feature squished our points into a very thin line. So you can tell that, depending on how you look at it, there's not much variance in this direction, right? This direction describes almost all the spread for this particular relationship. So PCA is just going to let you know that this is the most important feature, and there's not a lot of variance here. Anyway, that's a bunch of talk that's going to take too much of our time. So let's just get right into it. So we pull PCA from the decomposition, escalator decomposition, and run our fit. What is wrong again? What have I done? Oh yeah, I didn't tell it what to fit on. I'm sorry about that. My bad. So we're going to run this on X scaled. So okay, I remember when I started talking. As much as this is a very cool tool that we can use for a bunch of things, we need to remember that PCA is also an unsupervised learning algorithm that is as badly affected by distance and the dispersion of your data. So you need to scale data before doing PCA. Okay. Okay, we've done that. Next, let us try to visualize. Let's see how much variance is described by each of the PCA features. So we're getting PCA. These features now are the PCA features. These are not the features that we originally had, like 0 and 1 and all of that. These ones are transformed features. Right, so this is going to be PCA dot number of components, and then we plot it in the bar charts. I'm just going to breeze through this so that we can call it a night. Why are my fingers so jammy? Okay, so I'm going to plot this is what we're doing. We have like different PCA components, like principal component 1, principal component 2, etc., or rather principal component 0 and 1 and all of that. So I'm plotting each component against the variance that is explained by that component. And that means how much information about your data does variance. How much information about your data does this particular component contain, right? And let you know if it's important or not, because if you're not giving me information about my data, you're wasting time, you're wasting my space, and you're wasting my resources, and adding noise to the data that I train with in it. I just ran this instead of pressing enter. Let's plot y label. Let's call that variance. Let's describe variance or explain variance. Then let's put our x label and call that PCA features. Good. Let's show we've plotted, not the gibberish that we have there right now. Okay, so this is our bar chart. And this tells us that the first component, component 0, explains the most variance. Then component 1 explains, some. 2, less than that. 3, even less, very close to 0. And the rest are dots, as you can see, right? So this is where the dimension reduction part comes in. So we can now instantiate a PCA model instead of just calling PCA, because when you just call PCA, it does PCA across, or it gives you as many features as you have. So if you have 7 features, it gives you 7 PCA transformed features afterwards. So now that we've seen that, let's say 3 features should be enough. We can use that to reduce the dimension and discard the rest of this, throw them away. All right, so for dimensionality reduction, we're going to let's call this PCA model. Let's call this PCA model and say this is equal to PCA with number of components equal to 3. Right? Then we fit this. Again, we're fitting this on the scale data. Then let's call XPCA. So now we're getting new features, right? Instead of the X scales that we had, we're getting new features now. These are transformed features. I'm going to call them XPCA. That's features from PCA. That would be PCA model dot transform fit, and now we're transforming X scale, right? Okay. Done. What have I done? PCA has not actually transformed. Sorry. Transform. Okay, there we go. All right. So let's see if you did a good job, right? So let's get this. Let's run the same test with Marine and all of them. Let's copy this. Let's come here and paste it. So now I want to see if working with just 3 principal components is reasonable, if it gives a reasonable output, right? So let's change this from labels on scale to labels. You can't see my screen. Can anybody else not see my screen?
You can see your screen.
I can see the screen.
You can see the screen? Can everybody see my screen?
Yes.
Yeah, we can see your screen.
Okay, Rebecca, you may want to leave the meeting and join back. Okay. Okay, let's run through this. Let's finish this in under 8 minutes. Okay, where are we? Okay, yes, let's make this labels PCA. So labels PCA would be using now we use our KMC model with the new features that we've gotten from PCA instead of the regular X or the regular X scale, right? X scale, yes. So we're using X PCA now. Does that make sense? We're getting labels from fitting and predicting k-means on XPCA. And that's going to give us the 4. I'm going to change this to labels PCA. And change this to labels PCA as well. It's going to be K4. This is CT4. And this is CT4. Right. Did you miss any? I think that's everything, right? DF4, labels PCA, labels PCA. Well, if there's anything missing, we can be told. I think that's everything. Okay, let's see. That is not bad. So we have most of this in here too, just 9 of them outside. And most of these in 1, just 2 outside. And most of these in 2, just 5 outside. So that tells you that just picking 3 of these principal components does a good job, does a pretty good job of describing all of your data, describing most of your data anyway. Okay, let's try to visualize this with the first 2. Since these 2 describe the most variance, let's try to use these 2 to visualize it to see if it gives us a reasonable spread. Let's just copy what we have here so we can save some time. Don't worry, guys, this is the last one. I promise. So let's make this lowercase x. So don't replace that one. Lowercase y. It is going to be using our PCA values now. Okay. So we're taking from XPCA. From XPCA, we're going to slice this. Let's slice this. So we take all the rows of the first column, and this is already going to be a number array, so we don't need dot values. And then this is going to be this is going to be the next one. So this gives us principal component 1 and principal component 2, right? So we're going to plot the x's and the y's, and let's show. Okay, so we can see we have a very good spread. It actually, spreads it out, unlike the other one that we had that shrunk it into one line, right? Now let's color the points using the labels that we already have. So let's use C equals variety number. Oh, did I define variety number? I don't think I did. Let's define it here. So variety number would be, that's grains, right? Grains variety number of values. You guys know what I'm doing here, right? We have a column called variety numbers. I'm bringing out the values in there and putting it into this. So that we just have that column on its own as an array here. Then we use those numbers to color the points in our scatter plots. And there we have it. So we can see that even though we've twisted and rotated our features and all of that, PCA still maintains most of this information. Now let's go to this original one. Let's use that column number 5 that had a better spread. And let's do the same thing. Yeah, this has a reasonable spread. So, at the end of the day, the PCA 1 and 2 might be related to columns 0 and 5. But like I said, you lose that interpretability when you use PCA. So let's follow this with the writing on this as well. Let's see how much of the information is maintained. So you can see that the relationship between the data points remains the same, even though it sort of rotates it, right? It sort of contorts the points because it's changing the features, it's transforming the features, it still maintains the data and the relationship between those data points, right? Okay, guys, I think that is everything we need to cover for this breakout session. I'll share the notebook with you guys on the group for anyone that wants to go through it. Yusuf, please go ahead and ask your question so I can let you guys go. Sorry, anyone can drop off right now. If you feel the attendance, go ahead and drop off if you want to. Let me go and delete it from.
Okay. Good evening, sir.
Good evening.
Good evening, sir. Okay.
Good evening, I can hear you.
Thank you very much for taking us through today's class. I really appreciate it. So I have a question, and my question is, I have two questions rather. The first one is, how can I be able to get the recording of this class and the previous ones? That's my first question. And my second one is that, unfortunately for a while now, I've not been able to work on my classes as I should and my assignments because I was on a task initially. So I just finished the task. So I'm thinking of a marathon way of doing the classes I have missed for a while now. So please, how can I manage through it to catch up with where you are presently in class so that I won't be having doubt of, not getting some things you're explaining in class? Thank you very much.
Okay, that's a tough one. Ismail, I'm going to answer the question while answering Yusuf. First of all, what did you say? Recordings. Yes, for the recordings, unfortunately, I'm not sure right now. I would ask to see if it's possible to maybe get the link or something, but typically they are uploaded on YouTube, on the AICA YouTube channel. But I think there's a technical issue that's keeping the uploads from happening. So I'll get back to you if I get any feedback on that. But for our supervised learning class, the notebook is available. It's on the Discord channel. So you can go through it. I tried to put in some comments there to make it a little self-explanatory. So if you have any issues there, you can always ask on the Discord channel. Anyone can answer. I'm available to answer. Your other TAs are available. And we have some bad guys, some experienced people in our midst as well. Then for catching up, I guess it depends on how far back you are. If let's say you've just missed unsupervised learning, you can catch up because, and this answers your question, Ismail. This week, or rather next week, our assignment is going to be a project that covers unsupervised learning. So you're not particularly going through a new course. You just be consolidating what you've learned already and maybe doing a little bit of research for things that you need to learn. I think so. I think it's clustering on Antarctic penguins, but the assignments will go out latest by tomorrow anyway. Yeah, so Yusuf, since what you have this week is a project on unsupervised learning, it gives you some time to cover what you've not covered in unsupervised learning and then do the project, right? If you've already gone through all of the unsupervised learning course, the project itself should take you maybe a day or two. So you can use like most of the week to cover up and then use a day or two to finish up the project. Then we'll meet for the breakout session. If you are farther back than that, you are going to have a lot on your plate. You're going to have to find a way to be covering what is at the back and, still what we have before us. So I just hope that you're not too far back. If you're just 2 weeks back, last week was a project as well. It was a project on supervised learning. So if you already covered supervised learning, that should take you a day or 2 or 3, to cover it. It shouldn't take so long. Then after that, you have some time to go through unsupervised learning before jumping into the project for the week. Does that answer your questions?
Thank you, sir. It answers it very well. Thank you very much.
All right, then. Does any other person have questions, or are we all itching to go to bed for those of us in time zones where it's night? Any questions? If you have a question, you can just unmute your mic and ask. All right, then. Looks like we're all good. Okay, guys, thank you for joining and thank you for staying up till this point. I hope you got something or the other from the class. I hope it cleared up 1 or 2 confusions if there were any. And yeah, I hope to see you guys next week. Happy learning and happy coding. If you have any questions, if some questions come to you later, you're supposed to go to bed. All right, that's good. If some questions come to you later or you have some confusion down the line, please use the Discord channel. It's right there. Ask your questions, tag me, tag anybody. Even if I'm not there, we have, bad guys. So I'll share the link to, all right, thank you for reminding me. I'll share the link to the notebook. Or should I share it as a PDF? What do you guys prefer? Did the link work out fine last time? I think I shared the link last time. Link or PDF? You can type in the chat.
Yes,
Okay, either way,
the link is okay.
All right, that's cool. I'll share the link with that. I think there was a cell I moved down, so I'll find it and put it in the right spot so that people don't get confused. Okay, guys, thank you so much for joining. You can all drop off now. I hope you've signed the attendance. See you on Discord and see you next week. Chima, what link are you asking for? Attendance or the notebook? I don't even think he's here anymore.